Hello, this is the video for the assignment of week 3 of the Everything is the Same course. And I'm going to do what the teacher has told us to do, which is this experiment with the spring. I'm going to measure the spring constant using two different masses. For the spring I'm going to use this toy from my daughter. It's not a very good quality spring, but that will be enough. And for the masses I'm going to use this set of keys, and that will allow me to have two different masses, because what I'm going to do is to remove half of the keys for the second part of the experiment, so I will have also half of the mass. I have compared the mass of the full set with a mobile phone, which I know is approximately the same mass, and it is 80 grams. And when I will remove the half of the keys, I will have a mass of about 40 grams. And then also for the second part, I'm going to do what another thing that the teacher told us, which is somehow to extend the experiment and to generalize it. And what I'm going to do is to calculate what is the period of oscillation of the spring, and we will get to a interesting result, which is that this period depends only on the stretch length of the spring. It does not depend on the spring constant, it does not depend on the mass, it will depend only on the length of the string, which is stretched by the gravity of the mass. We will show what are the equations for this. What I'm going to do first is to measure the length of the string without any mass, because I will have to subtract that from the length stretch for the calculations, and it is 9 centimeters. Now I am attaching the full mass. Okay, I'm measuring the length, which is about 61 centimeters. And now now I have only half of the keys, so the mass is also half, which is 40 grams. Okay. And if I measure the new length, it's about 41 centimeters. Now let's go for the calculations. We have an initial length of 9 centimeters, and the length that the spring was stretched with a mass of 80 grams was 61 centimeters, but I have to subtract this, which gives me a total length of 0.52 centimeters. So to calculate the spring constant, we have to do K times 0.52, I mean this is meters, equals 80 grams, which is 0.08 kilograms, times G. So we get K of 1.54 newtons per meter. Doing the same for the second length, which was 48 centimeters, and we have to subtract also 9 centimeters, which is 0.39 meters. And let's do the same calculation, which is K times 0.48 is equal to 0.4 kilograms times G, which is, I'm using a value of 10. So K in this case is 1.03 newtons per meter. So you can see that the spring constant is not so constant. The spring does not obey too well the Hooke's law. It couldn't be used as a very good dynamometer, and this is probably because, as well, you know, it's a toy, and when the length is too big the spring cannot do so much force. But the result is more or less as we could expect. So for the second time of the video, I'm going to show you how to calculate the period of oscillation of the system, and to show that it depends, that period only depends on the length that the mass is, that the spring is stretched when it is in equilibrium because of the force of gravity. And for doing that we have to solve this equation that we have seen many times in the course, which is m times the second derivative of the length is minus k times x, x being the length. This gives a solution of the form some constant times a to g the square root of k over m. This is x. But we also know, because of the constitutive law of the system, that k times d, d being the length of the spring stretch, is equal to mg. So reordering the terms, we have m over k is equal to j over d. And we can replace it here, and we get that the length is something like this, where they're all constant except this term, okay, which is the length that the spring is stretched. It does not depend on the spring constant, and it does not depend on the mass that I have. It just depends on how much the spring is stretched. So let's do the calculation for the system as it is now. And so this is omega, where omega is 2 pi divided by the period, and this is the square root of g over d. So the period is 2 pi times the square root of d over g. So we see that the period is longer if the spring is stretched more because of the mass. So for this particular setup, we get a value of 1.24 seconds. Let's see if the prediction is reasonably correct. And for seeing it, we just okay. And if you have yourself a watch and like to help me with this, maybe you can get your own conclusion and see if the period is about 1.24 seconds as expected. Okay, thank you for watching this video.